And good evening, AP Physics students. Mr. Curson coming at you here. Going to talk about velocity selectors in Chapter 20. All right, so we are going to combine here an electric field and a magnetic field. So I've drawn a picture here. Imagine I have an electric field that's pointing up and a magnetic field that's coming up out of the page at you, okay? Well, and I shoot a particle into this region of space. A charged particle at that, right? Well, since this is a positively charged particle, there would be a force up on this particle due to the electric field, right? And there would also be, in this case, a force down on the particle due to the magnetic field. Why down? Well, because of the right-hand rule, right? If I put my hand in the direction the particle is going, curl my fingers up in the direction of the magnetic field, my thumb would point downward, okay? Now, in the special case that these forces are equal to each other, we could say F sub B is equal to F sub E, okay? Now, if these forces are equal, what would happen is this charged particle would pass straight through this area of space and go out the other side. Now, what if the particle instead was moving slow, so V was kind of small? That means B would be smaller, the force due to the magnetic field would be smaller than the force due to the electric field, and the particle would go up this way and crash into that wall. If V was large, the speed of the particle was large, the force due to the magnetic field would be larger than the force due to the electric field, and the particle would come this way and crash into this lower wall. But if it's just right, the force due to the magnetic and electric field would be equal to each other. And that occurs when QE would be equal to QVB, or more specifically, if I have an electric field and a magnetic field, the velocity that would pass straight through would be equal to the ratio of the two fields, okay? You guys can't see that here. The ratio would be V would be equal to E divided by B there, right? Because Q cancels out. So I can choose an electric field and a magnetic field such that I only get particles coming out of this opening that have a particular velocity I want. Hence the velocity selector idea. All right. Now this is going to help us in problem number 60, because in problem number 60 we're told that a particle is in a region that has a magnetic field, okay, coming out of the page, let's say, and this particle is moving in a circle, right? Because the force due to the magnetic field is pointing towards the center of the circle, okay? And since this is the case, it's moving in a circle, we could say that there's a centripetal force acting on it, and that mv squared over r is equal to q vb. Or, if I rearrange this a little bit, we would find that the velocity of the particle is equal to QBR divided by M. Let's see if that's right. So that square cancels with that. Yep, that looks right. So in problem 60, we have a particle, a positively charged particle, moving in a circle. And they tell us what the radius is and what the magnetic field is and the mass and the charge. And the question is, what kind of electric field could I apply to this region of space so that the particle no longer moves in a circle, but instead moves in a straight line? And to do that, we could use our velocity selector equation here and say that the electric field strength would have to be something like this, or the strength of the electric field would have to be the velocity that the charge is moving at times the strength of the magnetic field. Well, they don't tell us the velocity in this problem, though. So what we're going to have to do is figure out the velocity by using these equations over here. Plug this velocity in to this equation here and use that to calculate the strength of the electric field that we would need to apply to make this charged particle, this proton, move in a straight line instead of in a circular path. So if we plug this in here, we get E equals QBR over M times B, okay? Or this would be QB squared R over M. Here M is the mass of the proton. And if we plug in our numbers here, the charge on a proton is 1.6 times 10 to the minus 19th coulombs. We're told in the problem that the strength of the magnetic field is 0.566 Tesla. The radius of this circle up here, the problem tells us is 5.1 centimeters, or 0.051 meters. And what else do we got? We got the mass of the proton, right, would be 1.67 times 10 to the minus 27th kilograms. And if we plug all that in, we would get that the electric field strength here is 1.57 times 10 to the 6th newtons per coulomb. All right. So let's review kind of what we did there. We knew that if the particle was moving in a circular path, that the centripetal force would have to be equal to the force due to the magnetic field. We got an expression for how fast the proton must be moving based upon its charge, the radius of curvature, the magnetic field, and the mass. In this case, it was the mass of a proton. We then used our velocity selector equation, which really just comes from the magnetic force being equal to the electric field force. And then did a little algebra and plugged in our numbers. All right, nice work, physics students. Now, this velocity selector equation you'll want to use in the next couple problems when we talk about mass spectrometers. But the things you don't ever want to do, according to Gary Larson, creator of The Far Side, is fall into laboratory peer pressure. Oh, look at that. Oh, just try it. Just try it. Yeah. Yeah, don't ever drink stuff in the chem lab. All right, nice work, AP Physics students. We'll see you tomorrow.